So in the first question, I hope you're able to see the results there. For the first question, the answer is that the energy levels are anharmonic, and that's exactly why we want to use the Josephson junction, because remember that in case of a harmonic oscillator, we have energy levels that look like n plus half h bar omega, or they're equally spaced. They have the same spacing. But if you have the same spacing, then when you apply a microwave pulse, you cannot exactly set it to which state you want. So we use the Josephson junction to, in fact, make it anharmonic. So the answer is that the levels are anharmonic. They're not equally spaced. They're unequally spaced. If they're equally spaced, then, when you try to go from 0 to 1 or 1 to 2, they will have the same energy. So you will not be able to initiate and work with the qubits properly. So the reason that we use Josephson junction or the transmon is due to anharmonicity. So I think many of you got it incorrectly. So please go back and check. And then the second question, also a lot of you got it incorrectly. So remember that this cosine phi or cosine delta in the Josephson junction, we have a superconducting layer, another superconducting layer. These are state preparations, and then we have their macroscopic wave function as something like this, e to the power I phi a and e to the power I phi b. And this delta or phi is the relative phase difference, phi a minus phi b, between the two superconductors. So the right answer is that it is the relative phase difference. In fact, it is this relative phase difference that we are using as the generalized coordinate to express the Hamiltonian, or this is the generalized. Oh, I'm not sharing the screen. Or am I sharing the screen? I don't think I'm sharing the screen. Okay. I think now I'm sharing the screen. It is the relative phase difference between the top and bottom superconductors that we use as the generalized coordinate to express the Hamiltonian. So that is the main thing for transmon, right? So we discussed the mechanical analogy, right? And we saw how the transmon is basically coming between two superconductors, and how we could related to a pendulum, in the sense that the number of Cooper pairs is related to the length of the pendulum, whereas a phase difference, excuse me, between the superconductors is related to this angle of the super pendulum. Sorry, not super pendulum, angle of the simple pendulum, right? So I hope you guys are able to recall that. So that we also talked about squid. So in case of a Josephson junction, we have only one superconductor insulated superconducting sandwich. But in case of a squid, we have two of these. And the reason we use this, like we talked in the last lecture, this is just a recap, is it allows us to tune the qubit frequency by modulating the external flux. So a squid loop basically allows external magnetic flux into a tunable Josephson energy, and therefore tunable qubit frequency. And that's why we want to use the squid. And squid, if you don't recall what the squid was, I think there was a figure of the squid somewhere that I put in. Here. So squid is just essentially two Josephson junctions in parallel. So I could apply a magnetic field and use that to control. Now here we are controlling the phase difference between two superconductors in a single Josephson junction. But now I can control the phase difference between the two Josephson junctions within the squid, which is controllable by an external magnetic field. So now we can do delta 1 minus delta 2. That is, you have these two superconducting Josephson junctions. And let's say this is delta 1 and this is delta 2. I can control the difference between them. And I can also control the effective critical current. And this phi external is the magnetic field that we are applying to control the. So this means that the magnetic field is pointing into the plane of the paper, right? And so that's why the DC squid is very useful. I'm not going to go into more details here, but the key point that we made last time, and I want to repeat again, is what are we using as a qubit here? This is a generalized coordinate that we are using as a qubit. That is the relative phase difference. And this relative phase difference comes in because the way we prepare the state preparation in each superconductor is different. You have e to the power I phi A in one, e to the power I phi B in one. This global phase wouldn't matter if we had just one superconductor, but when we have two, the relative phase difference matters. And it is this relative phase that we're using as the dynamic variable. So when we say there are energy states, that energy states are related to this cosine delta. This Hamiltonian is related to cosine delta. So this is the dynamic variable here. So these are the energy levels corresponding to delta. So when we are switching between 0 to 1, what we are trying to say is that we are switching to these energy states that have to do with the relative phase between the top and bottom superconductors or two different Josephson junctions if you have a squid, right? And so this delta describes the collective phase of the Cooper pairs within the ensemble. So it's not a single phase value, like for example, if you have in case of the normal computers, but rather generalized coordinate. It provides a coordinate space for the qubit. So in general, something called Cooper pair box is just a Josephson junction. So when you draw the Josephson junction just like this without a box, that means it's an ideal Josephson junction. But in general, we draw the Josephson junction with a box around it. That means it's a realistic Josephson junction, which means you have to consider it like a capacitor, an ideal Josephson junction, and a resistor in parallel, right? And the resistor kicks in when I is greater than the critical current, and there is some charging energy that is represented in this figure as Cj, that is the Josephson capacitance, right? So this is called the simple Cooper pair box. So what you are actually doing here is you have a gate capacitance and you have a gated voltage. By tuning the gate voltage, you can make the relative phase, the delta, change. And that's how we can set the qubit from 0 to 1. But such a circuit is often sensitive to noise, charge noise. So you use, for a real transmode qubit, excuse me, you have a shunt capacitance here. So this circuit, the second circuit, is exactly same as the first one, except you put in a shunt capacitance to just basically shield it from noise. And again, all these have to be at millikelvin temperature, right? And we also talked about the conjugacy between the number of Cooper pairs and delta. So be very careful. We are not saying that, although colloquially when people talk about transform, they talk about Cooper pairs are tunneling from one superconductor to another superconductor. These are not single Cooper pair states. These are states of a macroscopic ensemble, and there is a relative phase difference. So if you do multiple measurements, right, these uncertainty relations, we have discussed them before, they pertain to multiple measurements. So if I measure multiple Cooper pairs multiple times, then I get a distribution, the delta n of that distribution, the delta of the relative phase distribution, those are the ones that are in uncertainty relations, like just like x and p. So here what we are working with is a well-defined delta, right? We are working with a well-defined delta, and totally we are putting this shunt capacitance in series here to reduce the large shunt capacitance, to reduce the charge noise. So we define phase delta, the relative phase difference, very well, and use that as a weakly anharmonic oscillator with the lowest two levels. That's the real transmon. And we briefly discussed how we make this transmon. So you have a silicon dioxide, niobium, or aluminum, whatever material you would like to use as your superconductor. You could use that. We're going to millikelvin temperature. So most of these materials, metals, superconduct there. So you make the islands. We put in a resist. You expose it to light and etch away, and you just do photolithography to make these two islands of niobium. These are the two superconductor islands, and then you can fill it in with oxide here, which would be insulated, and that's how you would make the Josephson junction. And this is how a real Josephson junction looks like, or a real qubit looks like. And what you do see here is, you sort of see some lines going in here. And if you zoom in there, you see these interdigitated microwave readouts. And in the center here, if I zoom in further, that center box, that's the two squids. That's a squid with two Josephson junctions that you see. And these things in blue rectangles, the interdigitated resonators, are for readout and for initiating the qubit, and the whole thing is immersed in sort of a dilution refrigerator. And if you look at it under the scanning electron microscope, this is how a single transmon qubit, the squid, and the Josephson junctions look like. And that's what is really making our qubit. And so this is just for revision, because a recap. And so today, what I would like to do is we would like to get into how do we use these transmon qubits to make quantum gates and quantum circuits. So before we proceed, are there any questions? Oh, there are questions in the chat. Any questions? No? Okay. Okay. So then in that case, let's open the, sorry. So again, so we're trying to use this Josephson junction, the squid with um, Josephson energy, the delta, as the qubit. So if you look at a simple harmonic oscillator, all the energy levels are equally spaced, because in a simple harmonic oscillator, we have all the energy levels are n plus half h bar omega. So if you look at the difference between 0 and 1 or 1 and 2, they're all half h bar omega. So if I were to apply some sort of light or microwave, then you cannot be guaranteed that you are accessing the particle only in 0 and 1 states. So for us, in order to be able to do quantum computing, we want to be able to make sure that we are accessing these 0 and 1 states. We don't want leakage into the second state. So instead of having parabolic potential, recall that we have a cosine delta. So if you look at the cosine delta, this is the superconducting phase, right? The red dashed line is the simple harmonic oscillator, and the blue line belongs to cosine delta. So that is slightly anharmonic. So then what happens is the energy difference between 0 and 1 is different from 1 and 2. So you maintain the delta in such a way, or you maintain the circuit in such a way that you can isolate only 0 and 1, and sort of uh, push these higher energy levels out of the way. So there is no leakage. So we are always sort of working with either the qubit is in 0 state or qubit is in 1 state. That's what we would like to do if we are to say colloquially. So let us say that we have set our circuit. That is, we have a gate capacitance and some gate voltage, which is grounded. And then I have my Josephson junction or a squid. whatever you would like to use. Um, so, so let's say we use squid, right? This is our real transmon qubit. So we are accessing only the bottom two energy levels, 0 and 1. So because we are accessing only the bottom two energy levels, then what we could do is we could simplify the Hamiltonian. We don't need to work with this entire Hamiltonian. This entire Hamiltonian is giving us all the energy levels. But we set our EJ, that is the Josephson energy. Recall that the Josephson energy goes like the critical current times phi naught by 2 pi, right? And so, and then I have the EC, right? And we have seen that that EC goes as the capacitance. It is related to some the capacitance of the gate plus the capacitance of the Josephson junction. And if I want, I can put the capacitance of the shunt. And so by adding these capacitances that I want, I can control the ratio between this EJ and EC such that I can get only these two energy levels. All the other energy levels become inaccessible, and I'm accessing only these two energy levels. And so we don't need to consider the entire Hamiltonian because we are not worried about energy levels above 0 and 1. So then what we do is we rewrite the Hamiltonian just for the lowest two levels as H naught is equal to H bar omega 0 1 by 2 sigma z. So here sigma z is like applying a Stern-Gerlach operator with a gradient along the z direction. That gives you 1 0 0 minus 1. So it gives you two different eigenvalues or two different energies. So one of these energy would be 0, another of these energy would be 1. So 0 would be one eigenstate 1 0, 1 would be another eigenstate 0 1. So this is an approximate Hamiltonian. The reason why we are doing this, why I'm going more into details into this transmon Hamiltonian is later on in today's lecture, time permitting, we will try to run code on the actual IBM supercomputer. And when you're running on the supercomputer, you need to know what you're doing, what is actually happening. Otherwise, you would not be able to tell what is real, what is not real, and what makes sense and what doesn't make sense. So what we have to understand is, at least get some superficial understanding of what this qubit is. How do I initialize it? How could I, make it switch between whatever state I want? And how could I actually do computation with it, right? Because we're going to use quantum computing to solve problems that cannot be solved with classical computers. For example, factorization is one such problem, right? So then some of the problems, how it's even if the quantum computer gives you an answer, it's still hard to validate it even with a classical computer, even with a good supercomputer. So you need to know for sure how this is working to make sense of whether what you're getting is right or not, right? So what we're going to do in this lecture is exactly do that we are going to see in and out of, at least in a superficial way, how do we set this, how do we initialize, and then how do we apply different gates, and how do I control these, and how do I calibrate it, how do I work with it. So from scratch we have set up the mathematical formalism, and then we have seen how to make this transmon. And now we're going to see, using this transmon, how I can actually make it work like a qubit, right? Are there any questions on how we're coming up with this Hamiltonian? Okay. So then the omega 0 1 is the difference between the energy levels 0 and 1. And the next highest energy level is 2. So we consider a parameter called alpha, which is related to anharmonicity. And that is given as the difference between omega 1, 2, which is the energy difference between level 1 and level 2, minus the energy difference between 0 and 1. Ideally, we want this to be much greater than 0, right? Because if it is 0, then that would be like harmonic oscillator. That is, the difference between 0, 1 and 1, 2 is the same. So when you apply a microwave pulse, you're not sure whether you're going from 0 to 1 or 1 to 2. You see what I'm saying? So you do not know how you are initializing it. So we want this omega 01 to be much greater than omega 12, right? Sorry, omega 12 to be much greater than or very different from omega 01, right? So how do we actually drive this transmon? So we have an external control, right? We use a gate voltage, or we could use a flux when we're using the squid loop. So you can apply a flux, magnetic flux between the squids, and you could use that to. And the way you apply the magnetic field is using current, and you could control the inductive coupling through squid loop or capacitive coupling through a gate voltage. So usually this is applied through a microwave. So the microwave has some sort of a voltage that drives it, right? That is a V drive. And then you have a drive frequency. We want this drive frequency to match the frequency difference between the energy difference between 0 and 1 levels. So when I drive it, right, I introduce this perturbation. See that this first term is coming from the transmon Hamiltonian, right, where we have two levels, 0 and 1. And then I am coupling that with a perturbation from the microwave that I hope you remember, the interdigitated wires that were connecting to the squid or the qubit. And I'm driving it with omega t, and we'll see what the sigma x is, the Pauli X operator. We'll see in a minute why we're doing that. So to look at how this perturbation from the driving, from the microwave driving, actually changes the Hamiltonian, what we are going to do is we are going to rotate our frame to look at the Hamiltonian. So to rotate the frame, recall our Schrodinger wave equation, that is IH bar d psi by dt, right, is whatever is a time-dependent Hamiltonian times psi of t, right? And we have our Hamiltonian here, right? And we define a rotating frame by defining this unitary operator, u of t, which is defined as along sigma z, right? But with omega d, because we're considering omega d equal to omega 01, right? So if I have a time independent Hamiltonian, right, that's how the thing would evolve, the unitary operator, right? So now we can differentiate this. So I can differentiate psi prime is equal to u psi. So when I differentiate that, I get d psi prime by dt is equal to du by dt psi plus u d psi by dt, right? But we know the value for d psi by dt from the Schrodinger wave equation, right? So d psi by dt is equal to minus I h by h bar psi, right? I move this I h bar onto the other side, and so I get d psi by dt equal to that. And so I could plug that in back here, right? And then that's exactly what we are going to do. That is d psi by dt is this. And when we plug that back in, we can also write the, so if I have U to be unitary matrix, that means U dagger U is equal to identity matrix, right? So then I could write, instead of writing psi, right, I could write this as U dagger psi prime, because if I multiply both sides by U dagger, this becomes identity matrix. So I would get psi, and I would get this to be U dagger psi bar. So this would be equal to minus IH by IH bar, U dagger psi prime, what we are trying to do is we're trying to derive a Schrodinger equation for psi prime of t. Previously, when we have transform, we do not have the time dependence. We isolated the two levels, but we want to make sure that I'm starting in zero level, and then I want to be able to switch it controllably to the first level or second, or bring it back to the zeroth level. So we're trying to develop a Schrodinger equation for the d psi prime by dt in the rotating frame. So we could then see that this d psi prime by dt is again the psi. I'm going to write it as u dagger psi prime. So then I would get du by dt. Was there a question? Du by dt, and we have u dagger psi prime, right? Plus u minus ih by h bar u dagger psi prime, right? And then you could just rearrange these equations and multiply with ih bar from both sides, and then basically then you get this equation that you see at the end. So on one side you have ih bar d psi by dt, and on the other side you have something in the bracket multiplied by psi prime. So recall, so compare the equation that we have at the end to the original Schrodinger wave equation, which looks like this: d psi by dt is equal to h psi of t, right? So compare the last equation here to this equation. Here we have psi, and on the other side also you have psi, but here we have psi prime. So this is simply the Schrodinger equation for psi prime. If I write h prime as u dagger minus ih bar du by dt u dagger, right? So if I did that, then my equation would be ih bar d psi prime by dt is equal to h prime psi prime. So this would be the Schrodinger equation for in the rotating frame. Am I making sense? Any questions? And we know the form of this u. So here u dot is simply the same thing as du by dt, just a simpler notation, right? So then I can evaluate first this u dot u dagger, right? Instead of du by dt, we are writing u dot. So I can evaluate this u dot u dagger. And u is, we saw that u is equal to e to the power minus whatever terms that we have put in here. So then we are going to use that, right? The exponentials are going to get canceled out, and because you have u and u dagger, so the exponential terms would itself get canceled out. But when you do the derivative du by dt, this term is left out. So when you have u dot u dagger, you get this term, right? And we can repeat the math and just expand it out, and so we get these extra terms. But what we are going to say is that we are okay. So we are going to say that we will ignore these last two terms that are oscillating too fast, 2 omega d, because we want to tune this omega d. This is the frequency of the microwave that we are driving it with. And omega 01 is the difference between the 0th and first qubit. So we want to make sure that this omega d is similar to omega 01. So we can ignore these higher harmonic terms at 2 omega d. So that is what we call as, I think Priyanka or Priyanshu, I think if you're writing on the screen, it is a little bit distracting. May I request that you may take notes, but because it is appearing on my screen, so it is not very clear. And it is, I don't know if you want to ask a question or you want to say something. Okay. So we can then rewrite the Hamiltonian like this. And so this omega r, which is related to the drive frequency, this whatever this is, if you recall, that is related to the voltage or the flux, whatever we are using. If we are using just a normal Josephson junction, we can use a voltage, a gate voltage. If you're using a squid, you can drive it with a magnetic flux. Either way, right? So, okay, there's something in the chat. Um, okay, no problem. So this is the drive frequency or the drive that we are going to use to set the qubit. So here the reason I'm showing you this is we are ignoring these, but that doesn't mean that they don't exist, right? They are in there somehow, but we are just ignoring these. So these are the kind of things that would lead to leakage. Leakage meaning I ideally want to work with only 0 and 1 states. I want only 2 states for my information, 0 or 1. But we are getting this 0 and 1 by isolating these states that are present for relative phase difference delta, that is coming from the superconducting layers, by setting a certain gate voltage, or by setting something so that we can isolate these two gate voltages, these two energy states. But the second state, third state also exists. So there is going to be some transition to the second state. Recall that we, excuse me, recall that we defined an enharmonic parameter alpha, which is equal to omega 1, 2 or omega 2, 1 minus omega 1, 0. So this represents what we call as the leakage. And that's going to determine how good our quantum computer is. Because if I try to set it from 0 to 1, but it leaks to 2, then my quantum computer is not very good, right? Because then I cannot, really initialize. For us to be able to compute, we need to be able to say that I can initialize it into a particular state, right? And so you can think about this extra term now. This is the reason why we rotated our frame. So now the time dependence is gone here. So then I can now, at resonance, that is when my omega d, this delta that you see here, is related to omega 0, 1. That is the difference between, so in cosine delta potential, we have the 0th state and we have the first state, which we are isolating. And the energy difference is omega 0, 1. And we're driving it with microwave of frequency omega d. So on resonance would be, this is 0. That is our applied microwave frequency is equal to the difference between the 0th level and the first level, right? And the way it varies is given by this cosine phi. That is some angle, right? And sigma x and sigma y are operators like Pauli matrices. So we can say that the evolution is like a rotation. So at delta equal to 0, that is on resonance, the first term is 0. And then you have this term, which you can use as a unitary operator. So you have theta, which is given by, so recall that if you have a time independent Hamiltonian, we saw that I can write u as e to the power minus ih by h bar t, right? And psi at some time t is equal to u of t psi at some time t is equal to 0. So you apply the unitary operator on psi time t is equal to 0, and then you get psi at time t, right? So here our Hamiltonian when delta is 0 is simply this, right? So we have h bar omega r by 2, whatever in the bracket terms here, right? So my minus ih bar times t would look like something like minus I h bar sigma rt by h bar cosine phi sigma x plus sine phi sigma y, right? And so the h bars cancel out. And so you see this sigma rt this is what we are calling as theta. And this is the phi is inside the Hamiltonian is coming from the frame rotation when we did. We go all the way back. That is coming from the way we delay the input pulse, right? That is the phase in the input microwave pulse. So by controlling that phase and how long you apply the perturbation, this time t is how long I apply the microwave perturbation, I can achieve different gates. When I initialize it, it is in zero state, and I can do these different x gate, y gate. I can rotate it by pi by 2 along x, along y, and based on that, I can make the state 0 or 1 or a combination of 0, 1, so on and so forth. Are you able to follow me? Are there any questions? Okay, let's see in chat. No. Okay. So how do we calibrate this? How would we know what this omega 01 is? How would we know what this omega 01 is? Like for calculating, I could put it on a piece of paper and I can calculate it. But if I were to give you this transmon circuit and I asked you to find out this omega 01, how would you find out? Any ideas, any thoughts? Did you understand the question? If I were to give you a real transmon qubit and ask you to find this omega 01, right? The question is, how would we find out? Because we need to know what that is in order to do anything else. So we have to calibrate it. And the way we calibrate it is, there are multiple calibration routines. One is called the Rabi oscillations, right? So what you do in that, we'll see, you sweep some pulse, and from there, whatever results, you can figure out this omega RT by 2. And from there, you can figure out what is the energy difference. You can also do Ramsey experiment where you can figure out the difference between this omega 01 and omega delta. And we'll look at these two in greater detail. And you could do something called derivative of Gaussian quadrature, which we will not look at in much detail, but this is to suppress the leakage to, there is also the second state. So we apply the pulse with a certain shape in order to reduce the leakage to 2. So let's look at this Rabi oscillations, right? So when you have the qubit is driven by like a resonant microwave field, right? Then it oscillates between the 0 and 1 states. And that is what is called as the Rabi oscillation, right? So what we have is simply, the Rabi oscillation Hamiltonian would be omega r sigma z, because when you have, remember the Hamiltonian here, right? So we are just basically using this, right, to do the oscillation between 0 and 1. And so at any point of time, the psi is given by, this kind of a linear combination. So the probability of finding it in 0 or 1 is related to this omega r of t, where the oscillation frequency omega r is the Rabi frequency that depends upon the drive amplitude. So these Rabi frequencies are used to sort of calibrate what is the energy between 0 and 1. So you can think about the qubit like it has a spin, because here sigma z and sigma x are poly spin operators. So you can think about the qubit having two states that are like spin. And so usually what happens is that you're supposed to get something that is time that would just keep oscillating. It would just keep oscillating. It is like saying that if I pick a simple pendulum and let it go, ideally what happens is you have given it kinetic energy, so then it becomes potential energy, kinetic energy just keeps transforming from one type to another, keeps oscillating on and on. But in reality, it would stop somewhere because there is a drag or there is friction that is dissipative. So it would stop somewhere. So similarly, even these oscillations, even at the quantum mechanical level, there are some dissipative elements which we capture as relaxation or dephasing. So the relaxation time is called T1 and the dephasing time is T2. And because of that, it sort of decays. The probability amplitude is not the same. It doesn't remain as sine squared. It decays. And so by applying pulses that have different duration, you can obtain what is the energy difference between the two levels in the transmon qubit. So whatever oscillations that we are seeing, again, to recall, we are not looking at single particle oscillations. This is not a single Cooper pair that is oscillating between no Cooper pairs and one Cooper pair. This is rather related to the relative phase difference delta. So what is oscillating is the relative phase difference. And this oscillation means that we have identically prepared qubits under a coherent drive, right? And this damping arises from the statistical spread in frequency across repeated preparations, right? Identically prepared system. We are not talking about the state of a single particle. We're rather talking about an ensemble. So that's how we apply a rabbi gate to determine omega 01. This is the first thing you would need to do. But of course, when you are working with the quantum computer, you don't need to do this because it is built in. Just like how when you buy a laptop, you're not going to do all these things. It comes loaded with all the operating systems and all the things. But this is how one would do it if they were to build a quantum computer. The first thing you would be to do rabbi damping, calibrate, and understand what is the difference between the first zero and first energy levels. Then there is another experiment that is a Ramsey experiment, and this measures the phase coherence again and also determines the transition frequency. You do the same thing again. You apply pi/2, let it evolve freely, and then apply another pi/2 pulse and measure it. So when we say pi/2, what do we mean? Is remember that we had our Hamiltonian to have terms something like h bar, omega r, something, right? So this omega r again is related to the drive voltage or the flux, so on and so forth. So if I have a state psi, it's going to evolve at time t based on e to the power minus iht by h bar times psi at t is equal to 0. So this minus iht by this ht would have terms that look like sigma r t. So when we say pi/2 pulse, what we mean to say is that the sigma rt is pi/2. Right. So when we know the rabbi frequency, which we can determine from these kind of experiments from rabbi damping, right? So it gives us the rabbi damping or rabbi frequency. Then we know how long, what is the time scale that I need to apply the pulse for to get pi/2, right? So you apply it for that long and let it evolve freely, and then apply again another pi/2 and measure, right? The first pulse basically gives you a coherent superposition between 0 and 1. And during the free evolution, basically then the first state is going to decay. If you apply a perturbation, it's going to excite it from 0 to 1. But during the free evolution, the first state is going to decay. And that is going to decay with the original Hamiltonian of the 2-qubit system, which is, again, the energy difference between 0 and 1 coupled with sigma z. So then you would get the total state to be like this in that free evolution state. And then we apply another pi/2 pulse and then measure the probability. And whatever that probability is must have this omega 01. And so by looking at the probability, the measuring. So we begin with a zero state. We apply one pi by 2 pulse, let it freely evolve, another pi by 2 pulse, and measure the probability of finding the state in one. And that's how we can measure this omega 01. Right? Again, when we say, whenever you hear in quantum computing that you are applying pi by 2 pulse or pi pulse or whatever pulse, what that means is you are applying the microwave pulse for a certain duration of time, so that based on the Rabi frequency of the oscillations between the two states 0 and 1, you would get the state to be in one particular place, right? Are there any questions? Are we going too fast? Are you able to follow? I don't hear anything back. Could you please let me know whether you guys are following me or am I going too fast, too slow? Are you with me? Okay. Okay, that's great. So now, if you want to implement something called an X gate, right? What an X gate is going to do is you begin with state 0, and I want to turn it into 1. If I start with 1, I want to turn it into 0. So it is like a NOT gate, right? We're going from 0 to 1 or 1 to 0, right? So we know that our perturbation that we are applying with our microwave uh, resonator is something like this. And this omega t is related to the Rabi frequency between 0 and 1. So our unitary evolution operator is related to this omega RT by 2. And we want this to be pi. So when we say that pulse duration is pi by sigma r, right? So imagine I put e to the power minus I sigma r. If I applied for pi by sigma r time, right, then I would get pi by 2 sigma r, right? So I would get e to the power minus I pi by 2 sigma x. And when we did the basics of quantum mechanics and we did some codes, I showed you how to do this exponential with a matrix. The sigma x is a matrix. So if you don't recall it, you can go back and maybe take a look at that. And so when you apply this pi by sigma this pulse for pi by sigma r duration, then you get X gate, that is, it rotates from 0 to 1. And in practice, we basically use Gaussian pulse from the microwave resonator, something that looks like this, to make it go from 0 to 1. So similarly, what we could do is we can apply some resonant pulse, but shift the by pi by 2. If you do that, then basically you have an extra phase coming in here, pi by 2. That is like rotating around y-axis by angle theta. And if you don't do any rotation at all, then basically that is called the Z gate. So these are some simple single qubit gates where you can go from one state to another state, right? So then there is the Hadamard gate. Hadamard gate, what it does is it starts from the 0 state and creates a superposition state that looks like 0 minus 1 or plus 1. So that's what the Hadamard gate does. And the way we experimentally realize that is, again, by applying a pi by 2 rotation, a pi rotation around x and a pi by 2 rotation around y. So you will be seeing, whenever you look at quantum computing with transmons, you will see these kind of terms like pi rotation and pi by 2 rotation. What they actually mean is that your perturbation coming from the microwaves is itself I to the power something like this. And so you apply it for a time t, so that this entire term is pi by 2 or pi, such that you get the gate you want, right? So far what we have done is we saw what is a transmon, how I can initialize it, and after initializing it in 0, I can make it switch to 1, or if it is in 1, I can make it switch to 0, or if it is in 0, I can set it to a positive combination using Hadamard gate, or if it is in 1, I could set it in another combination that looks like this. But the most important part is, how do we measure it? How are we going to read the qubit? So we need three components: a way to initialize the qubit, and the qubit itself, and the way to read the qubit. So the way we read the qubit is, this qubit is actually embedded in a resonator, and it is isolated from the environmental noise using something called Purcell filtering, which we are not going to go into. But in this technique, which is called the quantum non-demolition readout, the resonator itself has a frequency that it supports based on how we make the resonator. And measuring the resonator response reveals what the qubit state is, right? And so you can think about going back to the actual full transmon equation. Instead of the Hamiltonian, we could write the Lagrangian. That is, so Hamiltonian is, if I were to write it in a very crude way, kinetic plus potential, and Lagrangian is T minus V. And so here the V term would look like minus EJ, some cosine something. So that term in the Lagrangian would look like plus. So that's why you see plus here. And then here you have this phi q minus phi r, that is the qubit phase versus the resonator, right? And this is due to the coupling between the resonator and the qubit. And so you can derive, you can do all this, which I'm not going to go into. Ultimately, basically, what you get is this thing called Jaynes-Cumming Hamiltonian, which talks to you about how you are actually reading the qubit. So if this wave, when the microwave pulse is applied, the resonator frequency shifts either up or down based on whether you have the qubit to be in 0 state or 1 state, because of the way this Hamiltonian is. So you get a state dependent response on omega r. So when you have 0, you get one way. When you have 1, you get the other way. So that's how we measure the qubits, and the transmitted signal is then digitized, and that's how we get whatever we get, 0 and 1, right? And whenever we initiate the circuit that we want to work with, we initiate a classical bit along with the quantum circuit. Along with each qubit, we have a classical bit in which we are going to store the information about the measurement on the classical bit itself. And so the measurement chain looks like readout, tone sent to the resonator, and then there is a reflection of whatever wave you send from the Josephson junction or from the transmon, and based on that state reflection, you can determine whether you have state 0 or state 1. So again, to recall the ensemble interpretation, we are not looking at each single shot. Each single shot will give you 0 or 1. We need to accumulate multiple such measurements, and what we are looking at is only the expectation values, right? We are only looking at expectation values. We don't look at individual outcomes as such. So readout is a statistical measurement of the ensemble rather than a single measurement. So the total Hamiltonian then for the transmon qubit looks like this, right? Where the first term is the qubit itself, And the last term is, setting it. That is, I can put it into 0 state, 1 state, Hadamard state, whatever state I like. And then these two Hamiltonians are for, parts of the Hamiltonian are for the coupling that to a resonator, which we can use to read the state, right? So if you roughly look at what kind of frequencies are used in the IBM computers, we have the qubit frequencies around 5 gigahertz that relates to a period of 200 picoseconds. The resonator frequency is around 7 gigahertz. And the coupling between um, the qubit and the readout is around 50 megahertz. So it takes around few nanoseconds for us to read. So if your state is not coherent enough, that means I set a microwave pulse that has omega 01 energy. So then when I apply the microwave pulse, the system gets excited. But then what happens if you don't read it fast enough? It's just going to decay, right? So you want this readout to be very fast, and you want the coupling rate to be very fast to allow for fast readouts. So in general, currently what we are able to achieve experimentally in terms of relaxation time is on the order of few microseconds, which is much, much greater than the traditional values that are required for reading this qubit, right? So this is how the total experiment looks like, that you have these multiple things. So for example, if you have one qubit, this thing that is shown in red is the actual qubit. So you have the drive, you have the microwave frequency come in, that drives the circuit here, or you can apply a current by which you can control the phi or the bias here. And so that's how you can set the 0 qubit or 1 qubit. And then the gate capacitance is related to a LC circuit or a microwave resonator, which acts as a readout. So if this is in 0 state, the frequency of this is upshifted. If it is in 1 state, the frequency of this is downshifted. So you can see here for 0, it is omega r plus chi. For 1, it is omega r minus chi. So the omega belongs to this LC circuit, and LC circuit acts like a harmonic oscillator. So you have the readout resonator here. This is an actual qubit, right? So this transmon, although you see the plus, right? Basically the superconducting, the squid may be very tiny in here, right? So you can either apply flux bias or you can apply voltage bias, whichever way you want. And that's how you can initialize the qubit. If you want to couple two qubits, then you have qubit 1 that has DC quid, whatever gate capacitance, shunt capacitance, and a readout resonator. We couple them using another LC oscillator, right? So this is called a bus resonator. It has a capacitor and an inductor. And here you have two more capacitors. You use this to combine qubits. So all the qubits in practice, like you see here in the figure, are sort of coupled. So we can then initialize not just one qubit, but multiple qubit. Okay, sure. Somebody wants a circuit diagram repetition. So this red part is the actual qubit that we have seen so far. This is the squid part, right? This could also be Josephson junction, just one Josephson junction with a box. But here we are using the squid one because you can control it either with flux bias or by applying a voltage drive, either way. So this is what is used to, the red part is where the qubit is, and that qubit comes from the relative phase difference between these two Josephson junctions that are shown as X. And this is a resonator that is made up of some inductance and capacitance. Based on whether this is in 0 state or 1 state, this resonator frequency would shift up or down. And so by looking at these resonator frequencies shifting up or down, we can say that the qubit is in 0 state or in the 1 state. Does that help, Satvik? Okay. And then we have our 2 qubit state where we have, same 1 qubit black, 1 qubit blue, and we add an extra bus resonator. This is called a coupler high frequency bus resonator that sort of couples the um, uh, 2 qubits. So if you have 2 individual qubits, then you have simply the 2-state Hamiltonian for each qubit. But then if we want to entangle them, we want to add this coupler. So if I have a single qubit, I have h bar by omega 2 sigma z. But if I have 2 qubits, then I'm going to write that as h bar I, whatever is between omega 0 to sigma z1. This is what is acting on the first qubit. And then we have a similar term that would be acting on the second qubit. And so that would be the unperturbed Hamiltonian. And we couple these two through the resonator, through the bus resonator. So this bus resonator is represented by this part of the Hamiltonian, where G is called the exchange coupling, which is mediated by the capacitance in the bus resonator. So this is how we create 2 qubit states. So each of this has, so each of these things has a val. So we can go between 0 and 1 state, 0 and 1 states. And we're coupling them through the bus resonator. So then we can use different types of gates. Like for example, we could use I-swap gate where we can apply gate for a particular time. And just like how we saw it before using the unitary operator, we can make a swap gate that is 0 becomes 1 or 1 becomes 0. And if you have I-swap, that means you can create a superposition state sorry, an entangled state that looks like this, right? All right. So you can apply multiple different gates by controlling that, and so and you can just basically make multiple gates there. So these are the typical timescales that are involved. The coherence, the states stay coherent up to microseconds. Our reading and setting it happens in the nanosecond region, right? And so the biggest challenge with the gates here is that they're not perfect. They're not identical, ideal unitary gates, but they do have errors, right? So that can happen because we are not on resonance. That is, our omega d, the microwave frequency that we are driving with, is not really equal to omega 01. Or we can have the qubit relax too fast. That is, you have fast relaxation rates, or there is leakage to the second state, right? So because of these things, we get error. So we talk about fidelity. So if we have high fidelity, that means that we can trust whatever if your gates perform some operations to make your state going from 0 to some other state. Let's say you simply apply a NOT gate, right? You simply apply a NOT gate on let's say 0. How many times does it become 1? Are there times when it doesn't become 1? The times that it doesn't become 1 would be errors. And so using those errors, we can calculate the fidelity, right? We can experimentally characterize this. We don't need to sort of go into this. I will stop here for talking about qubits and how they can be changed with different gates, and see if you have any questions. Are there any questions? Okay. If there are no questions, let's do the quiz again. Oh. Uh, are you able to see the quiz? How about now? Okay. Okay, now you should be able to see it. Okay, we have only 12 people participating, so please, others, this quiz is to make sure that you're following what I'm saying and understanding and participating. So please make sure that if you are not at the screen, to come back to the screen and answer these questions. Okay. Um, I'm going to close the poll now. Okay, I still have somebody saying that the levels are exactly equally spaced in harmonic oscillator in a transmol qubit. We discussed how that is wrong, and I'm satisfied with the second question that you guys uh, understood that it is the relative phase difference. That's great. So now we have talked about all the boring stuff is done. That is, we know what a transmon qubit is, how we can experimentally do all this, all the stuff. We can actually that's okay, Abhilash. Um, uh, we can log into the IBM quantum computers in the next session and actually run these codes. So in the next session at 4:45, we have a tutorial where we will work together and run different gates on an actual quantum computer and on simulated quantum computer. And then I want you to draw conclusions to see whether single particle measurements make sense, or you need ensemble measurements, what they mean, whether gates are giving errors, and then construct things like Bell state where we can see entanglement. The beautiful thing is sitting right at your home, wherever you are, you can actually run this on an actual quantum computer. That's pretty cool to me. Imagine Bell or Einstein or anybody else having access to this sort of a thing. That IBM gives you 10 minutes of free time on these quantum computers that are at millikelvin temperature. So you can actually run a lot of experiments and write a lot of cool stuff, observations. You can write a lot of papers with it, if you're interested in doing research. So let's take a break now, and we will meet at 4:45, and we will do the tutorial on IBM quantum computing. Okay. Okay. Thank you. Yes, Satvik, it's pretty cool. It's millikelvin. Sorry, a poor joke probably. Okay, I'll see you guys at 4:40. Okay, so let's see what would happen, right? If we now apply the NOT gate twice, right? So I'm going to go up to the fifth cell where I have QC.X0, right? I'm going to apply it twice. I don't know if it will work. I'm just going to try it. I'm going to apply NOT and NOT, right? Now let's see what happens. So I'm getting 0 2000 times in primitive circuit. Then let's see what happens. So if it is a gate error, would I get a higher error or a lower error? We should get a higher error, right? Right? So let's try it. But I got a lower error, right? Or similar error, I would say 158, 18, 12. So can this be gate error? Were you guys able to do that? Apply the NOT gate twice, got lower error. I mean, I don't know whether we can say lower or a higher, but similar, some error we got. But it is definitely not much higher, not compounded. Let us run it again back to 1. I'm going to try it again to see if it is going to change. But the thing is, see how fake the simulator is. It is so fake. I sound like Trump now. But let's see. Okay. See, now again I got 319. Now I got higher error. And then you can go back to your IBM quantum platform and you can see under instances how much time is remaining. So it doesn't take much time, like it's running only like for 5-10 seconds, right? Applied NOT gate twice and you got 0.078. Okay. Okay. But we ran it thrice and it's coming back to the same error. Non-gate error. Then it's not gate error. Yeah. Okay. Is everyone comfortable with that right now? That everybody is able to see that you are getting in simulator all the time the same result, but not in real quantum computer. I hope all the time we spent last week makes sense to you now. Yeah? Okay. Yes. Okay, then let's move on to this thing and let us try different shots and see if there is any changes in different shots, which you can do later by yourself. But for now, we'll try to do exercise 1, right? We will run a Hadamard gate. As we discussed in the morning's lecture, a Hadamard gate takes, if you start with a 0, then it goes into 0 plus 1 superposition state, right? So you go back to the top cell where we created the quantum circuit, and then instead of X gate, we want Hadamard gate, right? Excuse me. We use H, and then I run it, and you should be able to see the Hadamard gate and the measurement. Is everyone able to do that? So Hadamard gate puts it into superposition. So I should get pretty much 50%, 50% when I run it on a simulator. Why is the simulator is erroring now? Because the Hadamard gate itself is preparing differently. It is not preparing the same one, right? So it is in the preparation, right? So it is because of the Hadamard gate. It is simulating the Hadamard gate, not just one gate. But it's still, you see yeah, it is supposed to be equal, but it is doing that because of the way we're running. So you can change the shots, and if you increase the shots, This is like coin toss. If you do 2000 times coin toss, you don't exactly get 450, 500, 500 or whatever. You get little bit difference. That is how you get. So that's what the simulator is doing. Suppose if I do, let us say, instead of 2000 shots, I'm answering Saptagiri's question. So if I run 10,000 shots, right? Eh? Okay, I have to change this to 10,000. So you see the difference decreases. Saptagiri, are you able to see that if you, it is due to the number of shots. Ideally, you need to go to infinite shots. So let's go back to 2000. And then let's see, make sure you're able to run. Yeah, it generates random numbers. That's right. So now let's run this part and see what it shows. 0.549 and 0.451. Right now you can change for this part, you can change the number of shots and compare, for yourself. We are not going to do that right now, but change the numbers and try to compare for yourself how that changes with the number of shots. Like for example, if you run instead of 2000 shots, if you run like 5000 shots or whatever number of shots, how that this probability change, right? If I were to make it only like, let's say, 100 shots, what would you expect? Would you expect the things to be very different? Saptagiri, why are you getting probability more than 1.0? I don't know whether that is right. Multiplying it by the wrong number somewhere, yeah. But yeah. So if that was the simulator or the, yeah, so but if you change the shots, it should automatically change in the experimental one, the probabilities. Okay, that's great, Shafna. But I defined in the experiment one, I defined shots, so it's not summing up to one somehow. N0, there is, okay, so let's remove this part. Yeah. Yeah, so in that shots, I had like whatever. I was trying to get it another way, but if you just change here this part, I highlighted it on the screen. Just change that as well, then it should work. So you see, I changed to 100 shots, and then I have 64% and 36%. Right. Okay. I hope everybody is able to do that. Is there anyone who is not able to run it on a real quantum processing unit? Why is the probability more close to equal on reducing the number of shots? Shouldn't that be opposite? No, it is not more close to equal. It is different. It is 64-36. Okay. Now the probabilities look better. Yeah, I mean it depends. It's not the same. That's the thing with the real quantum computer, that you get what you get. But in the simulator you get the same always. Um Now, the next thing I want to do is, so you guys can go back to the PDF and do this exercise of running it for multiple times and see what you see the difference between these two things. I want to go to second exercise where you create a 2-qubit state, right? And you can create a Bell state from a 2-qubit state. So when you create a 2-qubit state, remember that the rightmost qubit is the 0th qubit. So if we usually write our qubit when we write by hand, if we write as 0, 1, on Qiskit that will look as 1, 0. Please see Dr. Gargi's comment that when after our lecture you can play with it more and make plot for step number 8, right? And share with us. Please do not forget. We will also send an email, right? So to create a 2-qubit state, right? You need to create 2 qubits, right? And we want to measure 2 qubits. So now when you do 2 qubits, you can apply the gate either on the first qubit or on the second qubit. Okay, so let's see. I'm just going to create 2 qubits and 2 classical bits, and I'm going to apply Hadamard gate only on the 0th qubit, and I'm going to measure the 0th qubit and store it in 0th bit, and measure the first qubit and store it in the first qubit. I hope this works. Yeah. So you see that I'm applying Hadamard gate only on the 0th qubit. And then measuring 0th qubit, but also measuring okay, it is showing measuring the 0th qubit again. So measuring the 0th, okay. Let's see. I have to do it this way. Yes. So applying Hadamard gate and measuring the first qubit and just measuring the second qubit. Is everyone able to see that? So you can run now with the simulator. I hope this works. Yeah. So then you get whatever 0 and 1. So that's how you create a 2-qubit state. But our qubit state is not the state that we want. What we want to create is we want to create a Bell state, right? And we want to put it into this state. So try to yes, Mahesh. So what you should do is not 0, 0. So the first part here is the qubits you want to measure. So you measure 0th and 1 qubit, and this is 0, 1. Store them in 0 and 1 qubit. If you put 0, 0, that means measure 0, 0 again. Okay. And you can do the same thing here. You can also apply Hadamard gate on the first qubit if you want. So Hadamard gate and measure. Right. But see that these are not entangled. These are just 2 qubits. We did not entangle them. What we want to do is we want to create the Bell state. So please go back to the lecture notes, which we haven't shared the lecture notes, which Dr. Gargi will share. So this is the lecture notes we had in the morning. You should be able to see it on the screen. So I showed you the gates there. So this is the Hadamard gate, right? And we have ice swap gate. Yes, that's right, Mahesh. So in the first lecture, I thought, yeah. So see here, ice swap gate, square root of ice swap gate, you can get the Bell state. So figure out how to run this. I'm not going to give you the solution. In addition to ISOP, there is another way also to run it. So figure out how to run that so that you have enough information to figure it out. And you can ask GPT or you can ask Gemini or whatever you want to do. Figure out how to apply the ISWAP gate and create a Bell state, right? And what we will do is we will try to make some measurements on the Bell state and the singlet state. So I want to create phi plus this state and psi minus state, two states. Create two states, and we will measure with simulator and QPU and find the differences. So we will stop here for today's lecture because I want you to spend time to do exercise 2 and exercise 3 and see what results you get. So tomorrow, when we come back, please have these results ready because that will be very important for what we are going to do tomorrow. Tomorrow we are going to do EPR paradox and Bell's inequality. Dr. Gargi will go through that. So for you to understand that, please run these and have your results. And please try to send us the results if you can before tomorrow's lecture. And we will share the solutions with you after tomorrow in the lecture tomorrow. Are there any questions? Okay. So Subhanshu, the 10 minutes time is what you are getting to run for free. Yeah. So every time you run, the time is going to decrease. So you can run for on a quantum computer, you can run for free for 10 minutes. That's it. About 10 minutes you got to pay. Right? So that's the free time that IBM is giving. I showed that already. Yeah. But note that it doesn't take much time to run one circuit. So it takes like 1 second, 3 seconds. So we ran so many things, but it's still like 9 minutes, 34 seconds is remaining. And remember, we ran like 2,000, 4,000 shots. So you can actually do a lot with 10 minutes. Um, the only thing I would say is if you are using GPT to code, GPT codes thinking that you have paid access. So tell GPT you don't have paid access. So it is not supposed to use sessions. So if you use GPT, tell it that you cannot use sessions because sessions are only possible in paid, not in open access. So we're using open access. Satvik, I'm not sure why you are getting an error after pasting CRN. Um, I do not know. So maybe try to repeat again. Try to go from scratch and see. Placeholder was not removed. Okay. So was the placeholder removed, Mahesh? Sorry, not Mahesh. Satvik. Mahesh says placeholder was not removed. So so please, you have to remove the placeholder. Paste your CRN here. It's just a placeholder. So remove that. Okay. Thank you, Satvik. Okay, guys, I think I hope you're able to see, and I hope you enjoyed running it on the real QPU and see how simulator is different from real QPU. What we are going to talk about tomorrow is about Bell's inequality, entanglement, and I think there was a question on entanglement from Subhanshu. So we will see that tomorrow. You can actually simulate that on the quantum computer. Uh, so if there are no questions, we will stop the lecture here. And please do exercises 2 and 3 before the lecture tomorrow. Thank you. Okay, thank you, guys.